Dear fellow colleagues, I am Non Figueiredo and I am here to present to you a paper entitled Trustworthiness in Sensor Networks, a reputation-based method for weather stations. I hope that it can be helpful to you and your work, and I hope also to see you soon. Please enjoy. I will start this presentation by introducing the topic of trustworthiness. Then I will describe the weather data sources that we used in this study, detail the methods and solutions that we developed, and finally show the results and conclusions. In this paper, we address the problem of providing trustworthiness to systems in the context of weather station. This particular context suits the kind of scenarios that we address in complex sensor networks. Its information is vital, and these kind of sensors are prone to failures and are exposed to a variety of malicious attacks. Trustworthiness by itself is a complex term. It is a soft security measure and it is often related to fault-resilient systems. And we can also relate trustworthiness to data integrity and resource management. In this study, we adapted a reputation-based framework to the particularities of weather stations data using the concepts of self-data trust and peer data trust that will allow to evaluate if the data of a particular station can be trusted. In this study, we had used two distinct sources of weather data: the Portuguese Institute of Sea and Atmosphere, which provided official data through public APIs, and the website Weather Underground, which has a significant dataset of stations of any kinds spread all over the world. There was used data from a total of 376 stations, 134 from IPMA and 242 from Weather Underground. These sources have different sampling rates. IPMA stations report one sample per hour, and Weather Underground stations report at one sample every 15 minutes. We have performed an average to reduce the sampling rate from Weather Underground stations to one per hour. The data that both sources provide are quite similar, with samples from temperature, humidity, atmospheric pressure, wind velocity, and solar radiation. To compute the trust value of a station, we had used a reputation-based framework. The concept of self-data trust and peer data trust allows to determine multiple values of trust, making possible to identify which stations we can trust. The concept of self-data trust uses the data generated by the node itself to evaluate its own trust value. Peer data trust uses the data of peer nodes that, through opinions, determine if the data of one node can be trusted or not. To evaluate the self-data trust of one node, we perform a set of statistical evaluations. We make two distinct sets of evaluations. The first one uses an indexes analysis and checks if the dataset is not empty and if all values are valid. The second one checks if all values in the dataset are between the safety boundaries, avoiding invalid values to be considered as trustworthy. The self-data trust value is considered zero if any of these conditions are met: empty dataset, invalid values, and values out of specified boundaries, and 1 in all other cases. If a unit has its self-data trust at zero, it is automatically considered as untrustworthy. The peer data trust uses the data from peer nodes to determine the trust value of the node. Each peer compares its own data to the node's data and emits their opinion about its trustworthiness. All the peers' opinions are then combined and a final value of peer data trust is calculated, which will allow to identify if the data of that node is trustworthy or not. We adapted a reputation-based framework to mathematically describe an opinion and how opinions can be combined. One opinion is a tuple composed by three values: belief, disbelief, and uncertainty. All of these components are values from 0 to 1, and its sum must be equal to 1. To combine multiple opinions from the participant peers, we need to define a special aggregation operator that allows to construct the final opinion from the peers' opinions. This aggregation operation is performed taking in account this set of equations on the right that allows to compute every individual component of the aggregated opinion. More than a suitable framework to handle the trustworthiness values, it is important to be able to evaluate how two datasets can be compared. More specifically, as saw in the previous slide, how the belief, disbelief, and uncertainty can be calculated. To tackle this problem, we had to address two major issues. Two datasets must not only be similar in terms of values, but also they must be correlated. These two issues can be easily observed by analyzing, for instance, the value of temperatures from two distinct sensors. It does not make sense that two sensors shows for similar location different average values or temperature variances. However, the simple Gaussian representation of the values are not sufficient to guarantee that two datasets are similar, as two distinct Gaussian variables with equal mean and variance can be totally uncorrelated. For instance, if one sensor reports the same temperature at night and the other during the day, and vice versa, these two sensors have similar mean and variances, but they are not correlated. In fact, for two time series be considered similar, they must present similar means and variances and also present a high level of correlation. To address these problems, we use the Gaussian overlap to have a measure of the similitude of two datasets on mean and standard deviation, and use the Pearson correlation as a measure of the collinearity of both datasets. Please note that, regarding the Pearson correlation, it is only considered the positive correlations values, as a negative correlation cannot be considered as correct in this context. The Gaussian overlap and Pearson correlation values work together to provide a similitude measure of two datasets, allowing the peers to evaluate their values against the node values. To adapt these measures to the used trustworthiness framework, we use the presented set of equations. The belief component of the opinion takes the average value between Gaussian overlap and Pearson correlation values. To determine the uncertainty, we sorted the peers from the closest to the farthest and increased the uncertainty for units that are more distant from the node. With this strategy, we were able to give a special significance to the comparison procedure, as the most relevant opinions comes from the nearest peers. The disbelief is the remainder of the belief value, and the k-value is used to guarantee that the sum of all components are equal to 1. With these equations, each peer can compute its individual opinion on the node's data. With all peers' opinions, we can now determine the peer data trust value of the node and evaluate if it is trustworthy or not. The process to verify if a node is trustworthy is performed taking the displayed procedures. Firstly, we assess the self-data trust value by analyzing the data generated by the node itself. If the self-data trust value is different from 1, this means 0, the unit is automatically marked as untrustworthy. If the self-data trust value is 1, the peer data trust needs to be evaluated. To evaluate the peer data trust, firstly, we perform a sort to the peers where the closest peers come first. Then the self-data trust of each peer is evaluated, and there are selected the 5 closest trustworthy peers to continue the process. For each peer, it is computed its opinion on the node's data. After all peers emit their opinions, we aggregate them to generate the final aggregated opinion. A node is finally marked as trustworthy if the belief component of the aggregated opinion is higher than 0.5. Otherwise, the node is marked as untrustworthy. To validate our proposal, we perform the time shift test, where a node's data with a particular time slot is compared with peers in which its data was shifted. As comparing data from different days, we expect that the correlation between data decreases as the shift value increases. The table shows the peer data trust values of a single node, and it can be observed that only when no shift is introduced, the system was able to identify the unit as trustworthy. There can be observed that the peer's opinions and the aggregated opinions decreases its values as the shift value increases. We had extended these procedures to the global set of weather underground stations, and there was calculated the percentage of trustworthy stations for different time shifts. There can be observed in the graph that the highest percentage of trustworthy stations is achieved as expected when no time shift is introduced, and the percentage of trusted stations decreases significantly as the time shift increases, also as expected. It was also observed that we still have a high level of correlation, trusted stations, when we compare data with small shift values, and this was also expected. In the displayed graphic is shown temperature values of a station that was marked as an untrustworthy by the self-data trust assessment. The graph shows an invalid value around hour 22, making the self-data trust value be calculated as 0, so marking this unit as untrustworthy. Here we can observe two datasets from different stations that were marked as untrustworthy, graphic B, and trustworthy, graphic C. In graphic B, there can be observed that the station reported temperature values that are highly uncorrelated to its IPMA peers. The value of peer data trust for this station was computed as 0.10, below the 0.5 limit to be marked as trustworthy. In graphic C, there can be observed a station where presents data that are highly correlated to its IPMA peers nodes. Its peer data trust value was calculated at 0.89, which leads to be marked as trustworthy station. In this paper, we presented a reputation-based method adapted to the specifications of weather stations. We had showed how Gaussian overlap and Pearson correlation can be adapted to the self-data trust and peer data trust concepts, making possible to identify a station as trustworthy or not. As next steps, we will study more techniques to enrich the self-data trust calculation with sensor fusion methods. The peer data trust will also be revised to include the distance in the uncertainty calculation. Despite the particularities that weather data has, we are convinced that these methods can be applied in a variety of applications. Thank you for your attendance, and I hope that these methods can be helpful for you. For any additional information or collaboration, please contact us for our email contacts below. Thank you, and I see you next time.